Hello everybody. In this chapter we will study a three-terminal device named the bipolar junction transistor BJT. Three-terminal devices are far more useful than two-terminal ones, such as the diodes that we studied in chapter 3, because they can be used in a multitude of applications ranging from signal amplification to the design of digital logic and memory circuits. The basic principle involved in the use of the voltage between the two terminals to control the current flowing in the third terminal. This sketch here shows a simplified structure of the BJT. As shown in the sketch, the BJT consists of three semiconductors. I'm talking about the sketch. Okay. It consists of three semiconductor regions: the emitter region, N-type, the base region, P-type, and the collector region, N-type. Such a transistor is called an NPN transistor. Another transistor that exists, which is a dual of the NPN, as shown here. It has a P-type emitter, there's an emitter, N-type base on the N-type, and a P-type collector. And it's appropriately called a PNP transistor. A terminal is connected to each of these three semiconductor regions of the transistor with the terminals labeled emitter, base, and collector. The transistor consists of two junctions, two PN junctions. The emitter base junction, EBJ, emitter base junction, and collector base junction, CBJ. Depending on the bias condition, forward or reverse of each of these junctions, different modes of operation of the BJT are obtained, as shown in the table here. The active mode is the one used in the transistor if the transistor is to operate as an amplifier. Switching applications like logic circuits utilize both the cutoff mode and the saturation mode. As the name implies, in the cutoff mode, no current is flowing because both junctions are reversed bias. In other words, if both junctions are reversed, we are in the cutoff mode. However, if EBJ is forward and CBJ is reversed, then we are in the active mode. And the last mode is saturation, whenever you have both junctions in the forward bias. Okay? Now basically, to sum up, in chapter 4, in transistors, we will analyze and design circuits that contain transistors and resistors and DC sources. We will know how to deal with them. Also, we will know how the transistor can be used to make an amplifier. Let's begin. Now, we said that there are two types of transistors, NPN and PNP. NPN is drawn like this, and PNP is drawn like this. In order to differentiate between them, an NPN has an arrow going out of the transistor, whereas in PNP, an arrow is going into the transistor. Okay? Here are the three terminals, the base. So here you have a voltage base. Here it's voltage at the collector, VC. Here we have voltage at the emitter. We also have currents flowing through the terminals. The current here, it's called IC, collector current. Here it's IE, okay, and here it's going in with the arrow, and this is IB. I'm talking about this arrow. It's going with the arrow. Okay. Now note that the currents are always facing downwards, and IB is always in the direction of the transistor arrow. Okay? Now the voltage drop between this point and this point is called VCE. The voltage drop between this point and this point is called VBE. And lastly, the voltage drop between this point and this point is called VCB. Okay? Note that we are always having voltage drops that is positive from the upward side and the negative is on the lowest part. Okay? Now, if you note here, the difference between NPN and PNP is that the arrow is swapped and emitter is always with the arrow. So here's the emitter in PNP. This is voltage at the emitter, and this is voltage at the collector, and this is voltage at the base. The current flowing through the emitter is called IE, the current flowing through the collector is IC, and the current flowing through the base is called IB. And again, it's with the arrow, so IB is facing outwards, IB. The voltage drop between this point and this point is called VEC. Voltage drop between this point and this point is called VBC. And the voltage drop between this point and this point is called VEB. Next. Now, we said that we have three modes of operation: cutoff, active, saturation. How do we differentiate between them? We differentiate between them through the checks. How do we know that we are in the cutoff region? VBE, which is the voltage drop between the base and the emitter, it has to be less than 0.7. Now, if VBE is less than 0.7, this means we are in cutoff. Hence, all the currents will be equal to 0 ampere. There's no current flowing through the entire transistor. Now, in active and saturation, VBE is greater than or equal to 0.7, which is opposite this one, right? It's the reverse of this one, which makes sense. Now, the problem is not here. The problem is now if I want to differentiate between active and saturation. Both of them, VBE is greater than or equal to 0.7. So if we get VBE greater than or equal to 0.7, I cannot tell whether if it's active or saturation. So what should I do? What shall I do in this case? I have to check on VCB. If VCB is greater than or equal to 0, this means we are in active. However, if it's less than 0, it means we are in saturation. The same concept applies in PNP. However, the only difference is that if here we have a BE, here we're having EB. The reason why is that we have swapped the E and C. So all the letters will be swapped. And if you are in cutoff, all the I's will be equal to 0 ampere. Okay. Here VEB is less than 0.7. And for active and saturation, VEB is greater than or equal to 0.7. Whereas VBC is greater than or equal to 0 in active and it's less than 0 in saturation. You have to memorize these conditions. Now, next, what is in between active and saturation? There is a region in between those two. The region is called edge of saturation. The region is called edge of saturation. Here it is. It's edge of saturation. In edge of saturation, the voltage drop between C and E at this side is always equal to 0.3. So at edge of saturation in NPN, VCE is 0.3, whereas in PNP, VEC is equal to 0.3. Okay. Now, deep in saturation, if you are in deep in saturation, VEC is 0.2. VEC is 0.2 and VCE is 0.2 in NPN. Okay. Now, what's the difference between saturation and edge of saturation? Saturation and edge of saturation, they are the same. When I say saturation or deep in saturation, I'm referring to the same thing. Okay. Now, one more point before I give you the equations. VBE is always equal to 0.7 unless I am given a sample. What's a sample? A sample is whenever you are given a V at I. Do you remember this from chapter 3? This is a sample. Whenever you have a V at I. Here it's VBE and IC. Here it will be VEB and IC. We will see later. Okay, and that's a sample. Now, moving on, what do we have? What equations do we have in chapter 4? Now, this equation is very similar to the one that we had in the exponential model of chapter 3. IC is equal to ISE VBE over VT. This is exactly the same as this equation, but this form is for P and P. Hence, instead of VBE, you are going to have VEB. Okay? Moving on. IE is always equal to IB plus IC. How do you memorize this? Think of AB, the alphabet. A, B, C, D. B and C are always together. So IE is equal to IB plus IC. Two more equations for IC. IC is equal to beta IB and IC is equal to alpha IE. Beta can be calculated through alpha. So beta is equal to alpha divided by 1 minus alpha. And alpha is equal to beta over beta plus 1. Now, if you're analyzing a transistor and you found all the currents, there's a way to check whether your answer is correct or it's wrong. i.e., the current across the emitter has to be the largest number, and the current across the base has to be the smallest number. IC should be between IE and IB. Now, beta can be used only in two regions, active and edge of saturation. However, in saturation, you are not allowed to use beta. You have to use beta forced. Beta forced is always less than beta, and you can calculate it normally using IC and IB. It's IC divided by IB. Okay? Let's start solving questions. The question says, the transistor in this circuit has beta equal to 100. You can forget about this. And exhibits a VBE of, so we have beta equal to 100. We have VBE equal to 0.7 volt at IC equal to 1 milliampere. Design means find all the unknowns. The circuit so that the current of 2 milliampere flows through the collector, meaning IC is 2 milliampere, and voltage of 5 volt appears at the collector. So VC is equal to 5 volt. How do we begin? If you follow these steps that I'm going to show you right now, it will be very simple. Okay, always start by identifying the type of the transistor. Here, the arrow is leaving the transistor, hence we are in NPN. Next, put the labels on the transistor. This is step number 2. Here, it's VC, this is VE with the arrow, and this is VB. Here we're having IC, IE, IB. Okay. Next, put a list of all the unknowns. In order to remember it, think of it a list of the supermarket. You are going to go to the supermarket and you have to get all of these lists, everything on this list. And whenever you find one thing, you have to check it. What is the checklist? The checklist has to be at least six unknowns, which are the V's and the I's. Okay? Now in this example, also RC and RE are unknown, but usually minimum are 6, the V's and the I's. Now, After doing this step, the next step is to figure out the mode of operation. Which operation are we in? Which mode are we in? Are we in the cutoff, active, or saturation? So it's because we do not have numbers, it's better to assume. So first we are going to assume active. Okay, and when we finish all the unknowns, when we check all the list, we will check whether if it's active or not. If it's not active, we will recalculate everything again. How we are going to do this? I will show you later on. Now, so the first step I said is to put the type. Second step is to label. Third step is to list. Fourth step is to assume. Fifth step is to write that VBE is equal to 0.7, right? We said here VBE is 0.7 in all cases unless he gives me a sample. So in this question, do we have a sample or we do not have a sample? Yes, we do have a sample. Hence, VBE is not equal to 0.7. We have to recalculate it, okay? Because we were given a sample. How do I recalculate VBE? Through the equations. This equation is the only one that has VBE. Hence, I will write IC is equal to IS VBE over VT. If you remember from chapter 3, how did we used to cancel IS? We used to divide by the same equation. So here IC equal to IS VBE over VT. IS and IS cancel each other out. The numerator is the new, denominator is old. So what are we trying to find out here? We are trying to find VBE new, which is equal to VBE old plus VT ln IC new divided by IC old. Let's start substituting in numbers. VBE old is the sample, which is equal to 0.7 plus VT, which is 25 milli ln IC new. What's IC new? 2 milliampere divided by IC old. IC old is the sample, hence it's 1 milliampere. This will give us 0.717 volt. Okay. Now, after we have found VBE, the next step is to open VBE. VBE is equal to what? VBE is equal to the first letter minus the second letter. VBE is equal to 0.717. Do we have VB? If you note here, VB is connected to ground. Hence, it's equal to 0. So VB is equal to 0. Do we have VE? No, we do not have VE. Hence, it's equal to unknown, right? So we have to find it out. VE is equal to what? Minus 0.717. And now we have found VB, VE, VC, and IC are given. Okay? We have to find the rest. Okay, cool. After we have found VE, the next step is to find IE. Okay? If you found VB, then the next step is to find IB. So take it as a rule. Whenever you find a voltage, the next step is to find the current of that voltage. And if you found the current across a terminal, the next step is to find the voltage at that terminal. So now we are going to find IE. How are we going to find IE? Through Ohm's law, because we have a resistance. So IE is equal to VE minus 15 divided by RE. RE is unknown, so this cannot be solved yet because we have two unknowns, IE and RE. Let's think of another way. We have beta and we have IC, right? What can we find with beta and IC? We can find IB, correct? Or what we can do also, we can find alpha from beta. We can find alpha from beta and then use alpha with IC to find IE. Both works. Or if you want one more way, if you found IC through this equation, if you found IB through this equation, now you have two currents, IB and IC. Once you have two currents, you can find the third through KCL. Okay? Let's say that IC is equal to beta IB. IB is equal to IC divided by beta. IC is equal to 2 milliampere divided by 100. This will give us 20 micro. Now we can find IE. IE is equal to IB plus IC. IB is 20 micro, IC is 2 milli, hence the answer will be 2.02 milliampere. Now we can find RE. So here we found IB and IE. The only thing left is RE and RC. So RE is equal to VE, which is minus 0.707. Here I forgot a 7. Minus 0.717 plus 15 divided by IE. IE is 2.02 milli. This will give us 7.07 kilo ohm. That's RE. Now we have to find RC. How can we find RC? Now IC is known and VC is known, so we can do Ohm's law. We can say that IC is equal to 15 minus VC over RC. Hence RC is equal to 15 minus VC is 5. IC is 2 milli, and this will result in 5 kilo ohm. Okay? Now we have found all the unknowns. The only step left is to check, because all of these answers are based on an assumption. The check, now we assume that it's active, right? We have to check, and we are in NPN. So the check of active is VCB greater than or equal to 0. As I said before, that we cannot use greater than or equal to 0.7 because it's the same condition as inactive and saturation. But VCB can differentiate between greater than or less than 0. Okay? Now you can ask, why isn't it cut off? Cut off, we said that the currents are 0, right? But here in the question it said that IC is 2 milliampere. Hence, it's no longer cut off. It's definitely either active or saturation. So now let's do a check. We will check for, we said that it will be what? It's VCB greater than or equal to 0. VCB greater than or equal to 0. So VC minus VB has to be greater than or equal to 0. VC we found, actually it was given to us to be 5 volt. And VB, it was grounded, so it's 0. And 5 is indeed greater than 0. Hence, it's active. Now, we know that in active, one junction is forward and the other junction is reverse. Which junction is forward? Which junction is forward? The junction that is forward is the one with the arrow. So it will be BEJ. BEJ is forward. Always the arrow will be forward in both active and saturation. You remember? Here, in active and saturation, EBJ is forward. Now here we're having BEJ because it's NPN. Okay, in PNP it will be EBJ. Anyhow, let's continue. The junction that will be reversed is the one opposite to the arrow. So it will be this junction. Okay, this junction is C and B. So CBJ is reversed. And like this, we have finished analyzing a transistor question. Let's move on. In the circuit shown in figure, let's forget about the figure. Okay, I want to delete this. Okay, so the voltage at the emitter was measured and found to be minus 0.7. So VE is minus 0.7 volt, beta is 50, and we need to find the following. Okay, let's begin. So the first step is to do what? To determine whether this transistor is NPN or PNP. As the arrow is leaving the transistor, this means we are in NPN. And the labels are already there. So let's move to the third step, which is the checklist. We said it's the 3 V's: IC, IB, IE. Now, even though they want only 4, the other 2 will be simple. VE is given and VB is given, so it's the same thing. Okay. Fourth step is to do what? Assume active. And then we have to write the VBE is equal to 0.7 unless we are given a sample. Do we have a sample? No, we do not have a sample. Hence, VBE is indeed 0.7. The following step is to open the VBE. So it will be VB minus VE. VB is 0.7. VB is 0 because of the ground. And VE was given to us and it's minus 0.7. So did we figure anything out? No. We just stated the obvious that 0.7 is 0.7. Anyhow, let's continue. This did not help us to find any new requirement. We need to think now. If we have VE, I told you, if we're having a voltage, the next step is to find the current across that voltage. So we need to find now IE. IE is equal to what? It's VE minus 10 divided by 10K. What is VE? VE is equal to minus 0.7 plus 10 divided by 10K. And this will give us 0.93 milliampere. Now we found IE. We have beta. If we have beta, we can calculate alpha. Alpha is equal to beta over beta plus 1. So it will be 50 over 51, which is equal to 0.98. Okay? So IE is equal to alpha IB. Sorry, I think I messed it up, right? It's IC IC equal to alpha IE. Hence, we figured out alpha, which is 0.98, IE is 0.93 milli, so IC is equal to 0.91 milli. Okay. After finding IC, the only current left is IB. So we can either use the KCL, which is IE equal to IC plus IB, or IC equal to beta IB. Anyhow, so IB is equal to IE minus IC. IE is 0.93 milli, 0.91 milli. This will give us 20 microampere. Okay. After finding IB, let's now find VC. VC can be found through Ohm's law. We will say 10 minus VC over 5K. So IC is equal to 10 minus VC over 10K. So VC is equal to 10 minus 10K multiplied by, is it 10K or 5K? Sorry, it's 5K. $5K multiplied by IC, and IC is equal to 0.91 milli. This will give us 5.45 volt. We have found all the requirements. Now the only step left is to check whether it's really active or not. The check is, we are checking on VCB, and VCB has to be greater than 0. We will say that VC minus VB has to be greater than or equal to 0. VC is 5.45 minus VB, which is 0 as it is grounded, and this is greater than 0. Hence we are inactive. Now, which junction is forward and which junction is reverse? The junction with the arrow is always active, so it will be VBE. BEJ is forward, and reverse is the one opposite to the arrow, so it will be CBJ, reversed. Okay, let me tell you a way how to memorize which side is the check. Now the arrow is always equal to the 0.7. For example, here we said that VBE is 0.7. Check, this is B and this is E, so the arrow is the 0.7. The one opposing the arrow is the check, so here it's the 0.7 side. The arrow is the 0.7 side. This is the check side, and this is for the saturation. I will tell you, I will restate it later on when we enter the saturation mode, but keep it in mind. This is for the 0.2 and 0.3, if you remember these two numbers. Anyhow, now we have finished from this question. Let's move on. In the circuit shown in this figure indicates that VB is 1, VE is 1.7. What are the alpha and beta for this transistor? What voltage VC do you expect at the collector? So they are looking for, let's write them down, VC, VE, VB, IC, IB, IE with the alpha and beta. Okay, VB and VE are given. We have to find the rest. Anyhow, so the first step is to determine the type. So this is PNP, as the arrow is entering the transistor. Next step is to label. This is IE. We said, remember that E is always with the arrow. Here it's IC, and this is IB. IB is facing outwards because of the arrow. It should be with the arrow. Moving on, we wrote the list. Next is to assume active. Okay, and we have to say that the arrow is equal to 0.7. What is the arrow? The arrow is VEB. You need to be careful with this. VEB is 0.7. Okay, in PNP it's VEB. See, I wrote it here. VEB is 0.7, whereas in NPN it's BE. Okay, so VEB is equal to 0.7. Now we have to open this. VE minus VB is equal to 0.7. VE was given and VB is given. It's 1.7 and VB is 0.7. This is equal to 0.7. So we have just stated the obvious, that 0.7 is equal to 0.7. We did not benefit anything. Let's move on. Now, as we have the voltages, it's time to find the currents at those terminals. So IE is equal to what? IE is equal to 10 Ohm's law. 10 minus VE divided by 5K. So IE is equal to 10 minus 1.7 divided by 5K. VE is 1.7. This will give us 1.66 milliampere. Finding IB is equal to VB, because current is going downwards. It will be VB minus 0 over 100. K. VB is it's 1, so it will be 1 over 100K. This will give us 10 microampere. So we found out now 2 I's. IC is left. We can do the KCL. We cannot use the alpha and beta equations because they are unknowns. Okay, so we are forced to use this. IE is equal to IB plus IC. So IC is equal to IE minus IC. IE is equal to 1.66 milli minus IC. IE minus IB. So IB is 10 micro. This will give us 1.65 milliampere. Okay, we found now IC. VC, let's find VC. We can find VC through Ohm's law. So IC is equal to VC minus 10 divided by 5K. VC is equal to what? VC is equal to 5K multiplied by IC minus 10. 1.65 milli minus 10 will give us minus 1.75 volt. Okay, having negatives on voltages is fine. We found VC. What's left is alpha and beta. We can use this equation for finding beta. Beta is equal to IC over IB. So it's equal to 1.65 milli divided by IB, which is 10 micro. So we will get 165. Let's find alpha. We can find alpha in two ways. It's either beta plus divided by beta plus 1, or we can use IE equal to alpha IB. Both of them will give us the same answer. Let's use this 165 over 166. This will give us 0.994. It's very important to put the number in 3 decimal points, because if you just write 0.99, alpha equals 0.99, this means that beta is equal to 100. Try it. Convert 100, find alpha when beta is 100. You will find it exactly at 0.99. So when alpha is 165, alpha is no longer 0.99. You have to be more accurate. Okay? Now, moving on. For the circuit shown in this figure, it is required to determine the value of the voltage VBB that results in the transistor operating. Use beta equal to 50. Now we are in active mode. Did we check here? No, see, we forgot to check. So let's check. The check is, we said it's not the arrow, it's the terminal that is, the junction that is facing the arrow. So it will be VBC. VBC has to be greater than 0. Okay? VBC has to be greater than 0. Greater than or equal to 0. So VB minus VC, is it greater than or equal to 0? Did I write here equal? No. I missed them. Here I wrote it. Okay. So VB, what is VB? In this case, it's 1 volt. And VC is minus 1.75. This will give us 2.75 greater than or equal to 0. And this is correct, therefore active. And the two junctions, one of them is forward, the arrow is forward, which is EBJ. EBJ is forward, and the other one is reversed, which is BCJ. BCJ. Okay? Let's move on. So here, the question says that we are in active mode. So in this case, we should not assume and we should not check, because we were told that we are in the active mode. We were given also an extra information that VCE is 5 volt. So let's start. We are in part A, we are in active. Beta is 50. And VCE is 5 volt. Now let's start normally. What do we usually do? We find the type of the transistor. It's NPN. And then we have to label. The labels are already there, but let me write them again. VE, VB, and the I's are written except IE. Okay? Then we have to do the list. We have VBB, additional unknown. Okay? So, how do we start? We start with VBE to be equal to 0.7, which is the arrow. VBE to equal to 0.7. So, VB minus VE is equal to 0.7. VE is equal to 0 because of the ground. Hence, VB is equal to 0.7 volt. We found VB. Next step is to do what? To find IB. IB, let's find it through Ohm's law. We will say that VBB minus VB divided by 10K. Now VB is 0.7. VBB is unknown. And IB is still unknown. So we cannot solve it. We have to think of another way. Note that we were given this additional information. So VCE is equal to 5 volt, meaning that VC minus VE is equal to 5. VE is 0, so VC is equal to 5 volt. After finding VC, we can find IC through Ohm's law. So we will say that it's VCC 10 minus VC over 1K. 10 minus 5 over 1K. This will give us 5 milliampere. Okay, 5 milliampere. We found IC and we have beta. Can we find IB? Yes, we can. It will be IC divided by beta. Okay, so IC is 5 milli divided by beta 50 equal to 100. Sorry, no, wrong question. It's equal to IB is equal to 100 micro. Okay, IB was found, IC is found, so we're left with VB, we found it at 0.7, VC we also found, so we're left with IE and VBB. IE, easy, KCl, plus IC, IB is equal to 100 micro, and IC is 5 milli, so it will be 5.1 milliampere. And finding VBB will be 10K multiplied by IB, which is 100 micro, plus 0.7. This will give us 1.7 volt. So part A is done. Part B, we need to do the same for edge of saturation. Now, let's add a new page. Okay, so I would like to copy the same, copy, paste it. Okay, it's NPN. Okay, now let's write the list again. VC, VB, VE, IC, IB, IE. Okay, we need to resolve this question with edge of saturation. Now in edge of saturation, what do we know? We know that beta is the same, right? We can use the same beta as inactive, which is 50. Why is that? Because it was written here. Beta is the same in active and edge of saturation. Also note that in edge of saturation we have an additional information, which is CE equal to 0.3. Who is CE? CE is this side. Remember when I told you this side is reserved for the saturation numbers? So here beta is 50 and VCE is 0.3 volt. Let's continue. How do we usually start? We start with VBE equal to 0.7 and then we open it. VB is unknown, VE is grounded, hence VB is equal to 0.7 volt. Now let's find IB. VBB minus VB over 10K, but we got stuck because VBB is unknown. Let's open VCE. Minus VE, which is grounded, equal to 0.3, hence VC is equal to 0.3 volt. Now let's find IC. IC is equal to Ohm's law, which is 10 minus VC over 1K. 10 minus VC, which is 0.3 over 1 or 10K, 1K. This will give us 9.7 milliampere. After finding IC, we can find IB because of this equation. So IB is equal to IC over beta, 9.7 milli divided by 50. This will give us 0.194 milliampere. After finding IB, we can find IE. IE is IC over alpha. Finding alpha from 50, you will get 0.98. Okay, so IC is 0.3 divided by 0.9898. This will give us, sorry, IC is 9.7 milli. Okay, this will give us 9.9 milliampere. Great, let's find VBB. VBB is equal to VB plus 10K IB. VB is equal to what? 0.7 plus 10K IB. What is IB? 0.194 milli. So VBB is equal to 2.64 volt. Okay, no need to check because we were given the mode of operation. Great. Let's now find the last part. Deep in saturation. Deep in saturation means saturation. And note that we were given beta first. We cannot use beta, so we were given beta first. Okay. Add page. I will copy this again. Okay. And BN. Now we need to solve this in saturation. Deep in saturation, same thing. Beta first is 10. And in saturation, we know that VCE is equal to 0.2, okay? Which is the left side of the transistor. Here, VCE. VCE is always equal to 0.2 in saturation. In PNP, it will be VEC, okay? Let's continue. Let's first write the list. VC, VB, VE, IC, IB, IE, and VBB. So I'm going to start with VBE. VBE is equal to VB minus VE. 0.7 equal to VB unknown. VE is 0. 0.7 volt. Then we will find IB. VBB minus VB over 10K. We cannot solve it because we have two unknowns. Let's open VCE. VC is unknown, VE is 0, this is 0.2, so VC is equal to 0.2 volt. After finding VC, let's find IC. IC is equal to 10 minus VC, which is 0.2, divided by 1K. This will result in 9.8 milliampere IC. We found VB, VC, and VE is grounded. So IB is equal to IC divided by beta forced. We do not have beta. So it will be 9.8 milli divided by 10, which is equal to 0.98 milli, right? After finding IB, let's find IE. IB plus IC. It's 9.8 milli, 0.98 milli. Even though the question did not ask for IE, but I'm finding it just for for completion. It will be 10.78 milliampere. Okay, so let's find VBB. It will be 10K multiplied by 0.98 milli plus 0.7, which is VB. This will give us 10.5 volt. Okay, so we have finished this question. Moving on. Okay, great. Let's continue. We need to analyze this circuit. So we have to find all the unknowns. How do we start? We start with the type of the transistor, NPN. Next we label VC, VE, VB. This is IC, this is IE, this is IB. Okay, next we will put the list. Okay, and then we have to say assume active, right? Now, after assuming active, we need to say that the arrow is equal to 0.7. So it will be VBE is equal to 0.7, opening it. VB is 4, given in the circuit. 0.7. VE is equal to 3.3 volt, right? Awesome. After finding VE, let's find IE through Ohm's law. This is IE. It will be VE minus 0 over 3.3K. So it's 3.3 over 3.3K, giving us 1 milliampere. After finding IE, let's find IC, because we were given beta. This means alpha is equal to 100 over 101, giving us 0.99. Okay, so IC is equal to alpha IE 0.99 multiplied by 1 milli will give us 0.99 milliampere. Great. So IE, IC are known now. VE, VB is known also. Finding IB through KCL. The reason why I'm saying KCL, because note here, IC is going downwards. Okay, IB is entering, so consider this the transistor as a point. IC entering, IB is also entering, and IE is leaving. Hence, you can find it through KCL. Moving on. So IE is 1 milli minus 0.99 milli will give us 10 microampere. Okay. IB, we're done. We're left with VC. We can find VC through Ohm's law. So it will be 10 minus VC over 4.7K. 10 minus VC over 4.7K. VC is equal to 10 minus 4.7K IC. If you calculate this, you will get 5.35 volt. Okay. After finishing all the requirements, the last step is to check. We are going to check on the junction that is opposing the arrow. So it will be VCB greater than or equal to 0. VCB greater than or equal to 0. VC minus VB greater than or equal to 0. VC is 5.35 minus VB, which is 4. Hence, it will be 1.35 greater than or equal to 0. Yes. Which junction is forward? It's the arrow. Hence, it will be 4 minus VE. It will be BEJ. BEJ forward and CBJ reverse. reversed. This chapter is simple. Moving on. How do we start? We start by identifying the type NPN. Then we will label VC, VE, VB, IC, IE, and IB. Okay? Then the list. Next, assume active. Then we will say that the arrow is equal to 0.7. So it will be BE is equal to 0.7 volt. Okay. VB minus VE is equal to 0.7. VB is 6 given in the circuit. VE equal to 0.7. So VE is equal to 5.3 volt. After finding VE, let's find IE. IE is equal to VE minus 0 over 3.3K. VE is 5.3 divided by 3.3K, which is equal to 1. Sorry, it's not 1. It's obviously it's not 1. It's 1.61 milli. Okay, 1.61 milliampere. After finding IE, let's find IC through alpha IE. Alpha is equal to beta over beta plus 1, so over 51 equal to 0.98. So here 0.98 multiplied by IE, which is 1.61 milli. This will give us 1.57 milliampere. After finding IC and IE, we can find IB. IB is equal to IE minus IC. 1.61 milli minus 1.57 milli will give us 30 microampere. Okay. Now, after finding IB, we can find VE. VE is found also. What we are left with is VC, which we can find through Ohm's law. So IC is equal to 10 minus VC over 4.7 K. So VC is equal to 10 minus 4.7 K multiplied by IC. And IC is 1.57 milli. VC hence is equal to 2.621 volt. Okay. Last step is to check. We are going to check on the junction that is opposing the arrow, which is VCB greater than or equal to 0, VC minus VB greater than or equal to 0, C is 2.621, VB is 6, hence less than 0. For the first time, this check is wrong, not active. Therefore, we are in deep in saturation. We are in saturation, not active, saturation. Because here if VBC is greater than or equal to 0, we are in active, whereas if it's less than 0, we are in saturation. Okay? So what should we do now? We should repeat all the requirements all over again, because these numbers are based on the assumption that it's active. But now we are in saturation. We are no longer in active. So here we have to repeat saturation. We will repeat everything from scratch. But when you reach to the point that you are going to use beta, you have to stop. You can no longer use beta because you have to use beta first. So we will start with, normally we're going to start as we started here, VBE. VBE, which is equal to 0.7. VB minus VE is 0.7. VB was 6, yes, minus VE equal to 0.7, hence VE is equal to 5.3 volt. After finding VE, we can find IE through Ohm's law. It will be VE minus 0 over 3.3K. 5.3 over 3.3K will give us 1.61 milli. Okay. Now we have found IE. It's time to find IC. IC is equal to alpha IE. Now we are not allowed to use this equation. Why? Because we found alpha from beta. We said beta is equal to, we said alpha is equal to beta plus 1. And beta is no longer beta, it's beta first. So we have to think of another way. In saturation, we know that this terminal has a constant value, VCE. VCE in saturation is equal to 0.2 volt, right? So we will say VCE is equal to 0.2. Let's open it. We just found VE. So VC is equal to 5.5 volt. Okay. After finding VC, we have to find IC. IC is equal to Ohm's law, 10 minus VC over 4.7K. It will be 10 minus VC over 4.7K. This will give us 0.957 milliampere. Okay. After finding IC, let's write the list. I forgot the list actually. So IC is known now. VB is 6, constant from the circuit. We found VC and we found VE. And we also found IE. So we are left with IB only. So IB is equal to IE minus IC. IE is 1.61 minus IC, which is 0.957 milli. So IB is 0.65 milliampere. Do you remember the point where I told you that IE is always the largest number? Here, IE is always the largest, then IC, then smallest is IB. We haven't been checking this thing. Let's see. So IB, is it the smallest number compared to IE? Is IE largest? Yes, IE is largest. Then comes IC, and then the least is IB. Okay. Now let's say that the question asked also for beta first. How do we find beta first? It will be IC over IB. So it's 0.957 milli divided by 0.65 milli. This will give us 1.47, no unit. Okay? Great. We're done from this question. Let's move on. For this question, we haven't been given anything. So let's start by saying that this is NPN, then labeling, IB, then we will write the list. And then we will say assume active. After assuming active, we will say that VBE equal to 0.7, VB minus VE is equal to 0.7, VB is 0, minus E unknown 0.7, so VE is equal to minus after finding VE, we need to find IE. IE is equal to VE minus 0 divided by 3.3K. Okay, VE is minus 0.7 and 3.3K. This will give us IE to be minus 0.212 milliampere. Okay, so now we have a current in negative. This is a problem. We cannot have a negative current. Why is that? Now we have assumed active, right? Active, it means the currents are moving in this direction. Whenever we have a current to be negative, this means the current is opposing. Okay? Now what is a transistor? A transistor is a buildup of a diode. If you remember, if a current is moving in the same direction as the diode, then it's on. Okay? However, if the current is facing the diode, then we are in the reverse region. So whenever, take it as a rule, whenever you have a negative current, this means we are no longer in active because now the current is in the opposite direction. Okay? So which region are we in? We are in the cutoff. Whenever you have a negative current, then we are in cutoff. So we have to repeat everything. So remember, usually you're given a question, just start normally. Assume active and start solving. If you get all the requirements with no negative current, the last step is to check. If the check is correct, then you are in active. If the check is wrong, then you are deep in saturation. However, while you are solving the question and you got a negative number for the current, not for the voltage, for the current, then you are in cutoff. So this way you have covered all the three regions. Now for the edge of saturation, you do not go to edge of saturation unless the professor or the instructor tells you that you have to solve in edge of saturation. You by yourself, you don't go to edge of saturation. Okay? I hope this is clear. Let's go to cutoff now. Cutoff. In cutoff, what do we know? We know that all currents are equal to 0. See? All currents are equal to 0 in cutoff. And the check is VBE less than 0.7. Let's remember this one now. So all the currents are what? Zeros. IC equal to IB equal to IE equal to 0 ampere. Okay, we found all the currents. VB is by default grounded. VC will be 10. Reason being I equal to 0, hence resistance useless. Voltage here is equal to the point here, so VC is equal to 10. But you can find it through Ohm's law. You can say that IC is equal to 10 minus VC over 4.7K. So IC is 0, 10 minus VC over 4.7K, 10 equal to VC, so VC is 10 volt. Okay? And VE is equal to 0 because resistance is useless. This is 0 and this is 0. You can also prove it here. You will say that IE is equal to VE minus 0 over 3.3K. Or if you want to argue that it's going to in the opposite direction, it doesn't matter really because I is 0. So here it's 0 VE over 3.3K, hence VE is 0 volt. Okay, so we are done for this question. Let's say that you are not believing that this is in the cutoff mode. Let's do the check for cutoff and see if it's less than 0.7 or no. The check for cutoff is VBE less than 0.7. VBE is less than 0.7. VBE is less than 0.7, which is the arrow actually. The arrow, which is VBE, has to be less than 0.7. What is VB? VB is 0 because it's grounded, and VE is also 0. So 0 minus 0 is 0, and this is cut off. And both regions are reversed. So CBJ and BEJ are reversed. Okay, we are done for this question. Moving on. Now, how do we start? We start by the type P and P. Then we label next we will put the list. Okay, then we will assume active and say that VEB is 0.7 because of the arrow. VEB is 0.7, and then we will open it. VE is unknown and VB is 0. So VE is equal to 0.7 volt. Okay, after finding VE, IE is equal to what? 10 minus VE over 2K. So it's 10 minus 0.7 2K, which is equal to what? It's equal to 4.65 milliampere. After finding VE, let's find IC, which is alpha IE. Alpha is 0.99 and IE is 4.65 milli. This will give us 4.6 milliampere. Now we can find IB through the KCL. IE minus IC, it will be 4.65 minus 4.6, resulting in 46.5 microampere. Okay, after finding IB, let's find VC. We found the I's, E and B. Now IC. Last thing is IC. Sorry, VC. We will do Ohm's law. Minus 10 over 1K. VC is equal to 1K multiplied by 4.6 milli minus 10 equal to minus 5.4 volt. Last but not least is to do the check. Check is the terminal or the junction opposing the arrow, so it will be VBC. VBC greater than or equal to 0. VB minus VC greater than or equal to 0. VB is 0. VC is minus 5.4 greater than or equal to 0, so 5.4 is greater than 0, hence active. Now, this junction EBJ is forward and BCJ is reversed. Okay, two more questions and we will be done. Yes, let's solve this question. Now, type of transistor NPN, then we will label. This is VE. My handwriting is going dirty now. IE, this is VC, this is VB. Then the list VC, VE, VB. Okay, then we will assume active. Then we will say VBE is 0.7. Then we will open it. VB is unknown, VE is 0. So VB is 0.7 volt. After finding VB, we can find now IB through Ohm's law. We will say that IB is equal to 5 minus VB over 100K. So it will be 5 minus 0.7 over 100K, giving us 43 microampere. After finding IB, let's find IC through beta IB. Beta is 100. IB is here. This is beta. IB is 43 micro. So this is equal to 4.3 milliampere. Okay. After finding IC, we can find IE through IB plus IC. Okay. So it will be 43 micro plus 4.3 milli, which is equal to 4.34 milliampere. Okay. Now, IE. We're done with IE. What's left? We found also VB. Did we find VC? VE is known. We're left with VC. We can find VC through Ohm's law. We will say that 10 minus VC over 2K. So VC is equal to 10 minus 2K 4.3 milli, which is equal to 1.4 volt. Last step is to do the check. The check is on the junction opposing the arrow, so it will be VCB. VCB has to be greater than or equal to 0, so VC minus VB is greater than or equal to 0. VC is 1.4, VB is 0.7, so 0.7 is indeed greater than 0, therefore active, and the two junctions are CBJ reverse and BEJ forward. BEJ forward and it's CBJ reverse. CBJ reversed. Okay. Last question. Now this question is a little bit tricky. We need to focus here. Okay. Let me drink some water. Alhamdulillah. Okay. So how do we approach this question? We have beta equal to 100. We need to find all the voltages and currents. So the list VC, VB, VE, IC, IB, IE. Okay. First is first, so it's NP N. Next, let's do the labeling. This is VC, VE, VB. This is IC, IE, and IB. Okay? How do we usually start? We usually start by assuming active. And then we say that VBE is equal to 0.7. VB minus VE is equal to 0.7. VB is unknown, VE is unknown, so we are stuck. We cannot solve it. How do we approach this question? Whenever you see two resistances in the middle of the circuit and the rest of the circuit is at the middle between those two resistors, you have to do Thevenin. Okay, what is Thevenin? Thevenin is a voltage source, resistance and series, right? This is Thevenin. So we have to convert this design to Thevenin. How do we do it? It's very simple actually. You always do the same thing. For VThevenin, this is 15 volt. Okay, and you have two resistors, 100K and 50K. 50K, and VThevenin is in the middle and it's on 50K. Okay, so VThevenin is what? It's 15 multiplied by 50K over 50K plus 100K, and this will give us, I think, 5 volt. Yes, 5 volt. Okay, so now we have found VThevenin. We are left with RThevenin. How do we find RThevenin? Usually, in order to find RThevenin, we have to look from this side, and all voltage sources, they have to become short circuit and current sources open circuit. Here we have only voltage source, so we are going to do a short circuit, 100K. Okay, now if you look from this direction, what's the relationship between these two resistors? They are in parallel. Okay, if you are confused, just memorize. In order to find VThevenin, do a voltage division, and in order to do an RThevenin, do actually two resistors are in parallel. That's it. So here it will be 33.3K. After finding the Thevenin equivalent, the next step is to redraw the circuit. So here our VThevenin is 5 volt, RThevenin is 33.3 kilo ohm. Okay, and then the rest of the circuit. 3 kilo. Okay, here 5 kilo ohm, and this is 15 volt. Okay, now let's label this again. This is VB, VE, VC, IC, IE, IB is inwards. Now let's try the VB equal to 0.7 again. VB minus VE is equal to 0.7. Is VB known? Until now, no, because of the resistor. Okay, and VE is still unknown, so we cannot solve it through this equation. Okay, so we have to still think of another method. Now, what are we going to do? We have to do KVL. KVL is always, okay, with the direction of the arrow. So we have to do KVL in this direction. We have to do KVL in this direction with the arrow. Always when you find Thevenin, when you do Thevenin, the next step is to do KVL. Okay, so how do we do KVL here? We have to say minus 5 plus 33.3K IB plus, don't forget this arrow. I cannot stress this more. This arrow has a value, VBE, which is equal to what? 0.7, right? So please do not forget this while you're doing KVL. Plus 3KIE. Now you might ask the question, why not include VB and VE? Now VB is a point, it's not a voltage drop. You have to include, usually KVLs, they have to include all the voltage drops. Okay? Now, let's continue. Equal to 0 because we're done. So let's simplify this. This goes to 0.7. So you're left with 33.3 KIB plus 3 KIE equal to 4.7. This is the first equation. You have one equation and two unknowns. So we need to find another equation that relates IB with IE. Do we have an equation that has both IB and IE without introducing a new variable? Let's see. So we need an equation that has IB with IE without any new variables. If you take this, for example, it has IC. So now we didn't do anything. We have introduced a new variable. But if you take this and equate it to this, then they are equal. Okay? So beta IB is equal to alpha IE. Beta, so we have here IC equal to beta IB and IC equal to alpha IE. So beta IB is equal to alpha IE. Beta IB minus alpha IE is equal to 0. Beta is 100, IB minus 0.99 IE equal to 0. I got beta from the question, it said 100. Okay, so here we are having the second equation. If you solve this using the calculator through mod, I think it's mod 5.3, I'm guessing. Okay, you'll get that IB is equal to and IE is equal to. IB will be equal to 12.8 micro and IE is equal to 1.29 milliampere. Okay, now after you have found these two numbers, the question became easy. It's simple. Just find the rest of the list: VC, VB, VE, IC, IB, and IE. We found two. The third can be found through KCL. IE minus IC. IE is 1.29 milli minus IB, IB is 12.8 micro. And so IC is equal to 1.28 milli. Okay, so we found now IC. How do we find VB? We can find VB through Ohm's law. We have to say that IB is equal to 5 minus VB over 33.3 K. IB is equal to 5 minus VB over, so VB is equal to IB. What is IB? IB is equal to 12.8 micro, which is equal to 4.57 volt. We finished VB. Now VC and VE, we have to do the same thing, Ohm's law actually. So for IC it will be 15 minus VC over 5K, and for IE it will be VE minus 0 over 3K. IC is equal to 15 minus VC over 5K, so VC is equal to 15 minus 5K IC, which is 1.28 milli, yes, which is equal to 8.54 volt. Last is IE, which is equal to VE minus 0 over 3K. So VE is equal to 3K IE 1.29 milli. Yes, 1.29 milli. This will give us 3.87 volt. So after we found all the unknowns, the last step is to check on VCB. VCB has to be greater than or equal to 0. VC minus VB greater than or equal to 0. What's VC? It's 8.54 minus VB, which is 4.57, and this will give us 3.97, which is indeed greater than 0, hence it's active. So BEJ is forward and CBJ is reversed. BEJ is forward and CBJ is reversed. Okay, so we have finished the first part of chapter 4. The next part of chapter 4 is on amplifiers. It's also simple. See you in the next video. Thank you for listening.